Okay, some notes to fill in. Average acceleration is the rate of change. The rate of change of an object's velocity with respect to velocity with respect to time. So our average velocity is our change of velocity over a change of time, or VF minus VI, or TF minus TI, right? We're doing that line of, we just connect the two dots. What's the change in our velocities over our change of times? What are the units for velocity? Well, we're going to stick to meters per second, usually, but you're right, it can be kilometers per. So it's meters per second, which works out to be meters per second squared, or meters per second. Okay, so instantaneous acceleration is what we're going to use as the most, rather know what the instantaneous acceleration? No, at the very instant. So what at this moment exactly, what's my acceleration? Yeah. Okay, the derivative is the derivative of the velocity function with respect to everything is with respect to time. Just like time is our new x. Okay, so let's write this down first. So instantaneous is the limit. So our formula for our slope is change of v over change of t. We want that change of t to be really, really, really small. Approach 0. Right? It's our secant line. So really, are we going to use limits? No, because we know how to use derivatives. So it's going to be the derivative of our velocity function. Easy, right? V prime. Or it's a second derivative of our position. Yes. Of acceleration. Meters per second squared per second. It doesn't really, yeah, nothing really exciting. Okay, or it's the second derivative of our position. Yeah, it is the acceleration of the acceleration. Yeah, well, it doesn't really, yeah. Okay. All right. So the key is we're talking about velocity here, right? So velocity versus speed. What is velocity compared to speed? Vector. And now speed is our scalar. So when I give you -9.8 meter, I'm using 8, not 8.1. Don't be mad. You may as well just make it sad. So it's talking about magnitude and direction, right? So what direction is that moving? Usually, if we're talking about gravity, down. So we're going to use direction as well. The question, though, that we want to know is when is it speeding up or slowing down? We talked about this in Physics 10. Speeding up doesn't necessarily mean you have positive acceleration. And slowing down doesn't necessarily mean you have negative acceleration because of its a vector quality. So we need to look, acceleration describes the rate of change of velocity with respect to time. So if acceleration is greater than 0, then the velocity is increasing. Okay, so if our acceleration is positive, we can say our velocity is increasing. If it's less than 0, our velocity is decreasing. by using both the velocity and acceleration, we can determine whether the object is speeding up or slowing down. So if it both are positive values or both negative, so a times v, this is really important. This will be tested on. Okay, you'll be asked when is it speeding up and when is it slowing down, which is a very different question than when is the velocity increasing and when is the velocity decreasing. So know the difference between these two. So you can be traveling, so for example, downwards, right, is going to affect your velocity. A negative velocity would be downwards. Okay, so if V and A have the same sign, then we're speeding up. And I'm going to give you an example here. And if they're opposite signs, then we're going to be slowing down. So let's look at an example to try and... Do you remember learning about this a little bit? No? Okay. Well, yeah, it is physics. But let's look at this example where we have positive 4 meters per second squared. Okay? And so we're going to look here when velocity is greater than 0, and an example when velocity is less than 0. So velocity means velocity increases by 4 meters per second every second. Increases by 4 meters per second every second. Okay, so let's say at 0, we're going to start one with starting with a velocity of 10. And then we're going to do one of negative 10. So if my velocity is at 10, at 1 second, what would be my velocity? 14, good. At 2 seconds, it would be 18. Our velocity is increasing by 4 meters per second every second. So what's happening here with our speed? It's increasing, it's speeding up. So notice here, v was positive, and we had a positive acceleration, so a times v was greater than 0 here, it was speeding up. Say I started off with a velocity of negative 10 meters per second. So my position is negative. Now if I'm increasing by 4, what's my new velocity? Negative 6, and then negative 2. So what's happening with our values of our velocity? We're actually slowing down. Okay, so here our velocity was negative, we had positive acceleration, they were opposite signs, so their product was less than 0. We were slowing down. But then, yes, that's going to switch direction. Okay, again, let's do the same idea over here. Starting at 10 and negative 10. So this, what does this guy mean? Negative 3 meters per second per second. So our velocity is decreasing. By 3 meters per second every second. Okay, so at 10, now what's happening to our 1 second later? What's our velocity? 7, 1 second, 1 second later, I guess. 4. So we are slowing down. We had a negative acceleration and a positive velocity, positive direction. So a times v is less than 0. Here, this will become negative 13 and then negative 16, speeding up. Just because you're adding weird. So they're both negative, and then we were speeding up. On a graph, I'm going to show you how to spot that on a graph too in a little bit. A special name. Okay, do you want to try example 1? Yeah, why don't you give it a shot? Try example 1. Remember, S stands for distance, displacement, right? It's our position. Okay, it's not speed. Got to get that out of your head. Okay, what will the derivative of your position give you? Velocity. Okay, so that gives us 3t squared minus 12, and the derivative of our velocity gives us our acceleration, which is 6t. Okay, so our equation for acceleration is 6t. You found the velocity. So the acceleration at 3 seconds is 18 meters per second squared. And the acceleration at 5, 6 times 5 is 30. Okay, find the acceleration when velocity is 0. So first we have to find out when the velocity is 0. So how do we get velocity when velocity is 0? So when our velocity is 0, we have an equation for velocity. So velocity is 3t squared minus 12, and we want, when is our velocity 0? When we find that, we can figure out our acceleration. So you can either factor this, add 12, divide by 3, so 4, square root. Can you have a negative time? No, so the answer is just 2 seconds. All right, so what's the acceleration at 2 seconds? So acceleration at 2 seconds is 6 times 2, or 12 meters per second squared. Easy? What you need to know, so velocity of position, the derivative of position is velocity. The derivative of velocity is acceleration. S is distance. Okay. The position of a particle is given by, they even say the position. When is acceleration positive? So first thing we have to do is what? Before we can figure out when acceleration is positive, we need the equation for derive the derivative. Oh, I like that. Okay, so velocity, the derivative of our position, 4t cubed minus 12 times 3 is 36, plus 60t plus 5. And then you derive it again to get your acceleration. It's going to be awesome. 12t squared minus 72t plus 60. We can factor 12 out. Thank you. Okay, why do I want to factor this?
Make it more simple because 72 times the numbers.
Okay, we want to know, when is our acceleration positive? What describes something as positive? Greater than 0. So we want, when is this equation greater than 0? Right? When is it greater than 0? Because we want, when is our acceleration positive? So we have to factor. If I can factor out 12, is it 5? No, it's 6. 6. Thank you. Plus 5. Okay, two numbers that multiply to 5 and add to negative 6. Thank you. Negative 5 and negative 1. So what are our critical values? Okay, critical values are 5 and 1. What do we have to do when it's a product? Make a chart, right? Or you can even just use your little line test. Our critical values were 1 and 5. Now be very careful. With all of these problems, where does our graph actually start? 0. So you might even want to just go like this. Right? Because all of our problems, you don't have negative time. So we start at 0. Okay, so let's do our test. So our first critical value will have to be between 0 and 1. So maybe a half. So half minus 5 will give you a negative. And half minus 1 is also a negative. 2 negatives, positive. Now it's a quadratic, so we know negative and then positive. Okay.
Okay, next step.
Okay. So we want, when is our acceleration positive? What's our solution? When is our acceleration positive? 0 to 1 union. So we want positive, so I guess not including the 0, or not including the critical value, when it because at these points it's equal to 0. And then 5 to infinity.
Like in the real world, what particle is
Okay. Thank you. There you go. Okay. We're good? Now we can get to the graph stuff, which is the fun stuff. Can we move on? Okay. How are you finding this stuff? Okay. This is technically the easy stuff of the unit, so we want to make sure you're good with this. We're going to get to some applications starting tomorrow, which yeah, more, you'll see. Oh, trig. Okay, acceleration is the derivative of velocity. Thus, it is the slope of a velocity time graph. Okay, so this is a velocity time graph here. It says describe the motion. So from A to B, what's going on? It's positive acceleration. Why? The velocities are increasing. The velocity is increasing, right? The velocity time graph. The velocity is increasing, so we have a positive velocity. At B, or positive acceleration, thank you, sorry. At B, acceleration is 0. Okay, from B to C, it's a negative slope, right? So negative slopes, that means our acceleration is less than 0. At C, 0. And then from C to D, what's happening with my slope? Positive, therefore acceleration is greater than 0. Okay. Okay. This is new terminology. And we're going to use this a lot in the graphing unit. So we're going to talk about something called concave up and concave down. So recall velocity is the slope of a position time graph. I know this is really exciting stuff. Guys? Okay. So positive acceleration is when our slopes are increasing. I don't know how to spell velocities. Probably not. It's a weird word, velocities. It's not really a word, is it? The velocity. Is it? Okay, when the velocity, slope with the velocity, so the slopes are increasing. I'll just do that. Okay. Actually, we need a little room here because you have to draw a picture. Okay, so on a position time graph, this is what we call, this is a position time graph, okay? So I'm talking about a position time graph. This is a situation where our velocity is increasing because our slopes are increasing. So here we have a really negative slope, which is our velocity. And notice how our velocity approaches 0 and then gets more and more positive. Our slopes are increasing. That means we have positive acceleration. Okay? This is what we call concave up. Okay? So, if we have a position time graph, so this is, I'm trying to see, okay, when is our graph have positive velocity? So if I have something like this, so from this point, to say this point, it's kind of going down here, we would say that we know this is our position time graph, not a velocity time graph. I would say from this part, here to here, our acceleration is positive because the slopes are increasing. So what's the slope of this graph? Position time graph. What's the slope of this graph represent? Instantaneous velocity. So my velocity at this point is pretty negative, right? And then we do another one. All these instantaneous. Here it's 0. So all the way here, what's happening with my slopes? Becoming more and more positive. They're increasing. And so when our slopes are increasing, or velocities are increasing, that is positive acceleration. Right. Yeah, because it's really steep here. Yeah, it's coming more positive. And then the opposite, when the velocities are decreasing, we have negative acceleration. So here I have a really positive acceleration, right? Or velocity. Guys, come on. Okay, here my velocity is a little bit less, Now it's 0, my velocity. All through this portion, from here to here, the velocities are getting more negative. They're decreasing, and our velocities are decreasing. We have negative acceleration. And so this is when we have concave up, that's positive acceleration. This is what we call concave down, that's negative acceleration. The velocities are decreasing. Okay? Oh, wrong thing. So, when slopes or the velocity, so we're talking about a position time graph, specifically on a position time graph. The slopes or velocities, S, whatever, are decreasing. That's what we call, it's like a sad face, concave down. So we say concave up can hold water, concave down when poured on top sheds water. So if water was poured this way, it holds. If it's poured here, it would shed. It's just, yeah, okay. It doesn't get in. It doesn't, on concave down, it sheds it. It doesn't go in. Like it. Okay, happy face, sad face. Just go there, okay? Happy face. What type of a graph, on a position time graph, what would it look like if we have 0 acceleration? Line. Right, a line. Constant, right? It's constant velocity. So it's just going to be, oh, that's ugly. A line. Let's try this again. Okay. So straight line. So from a position time graph, we should be able to see when do we have positive velocities, and then when is our acceleration positive or negative. So let's describe this graph. So there's 2 parts to it. There's our velocity and then our acceleration. So I'm going to make a chart. So we want to do our velocity and then our acceleration. So we have A to B, B to C, C to D, D to E, and E to F. Okay. And F to G. Thank you. So first we're going to describe when our velocities are positive. So on a position time graph, basically if it's going uphill, it's positive velocity, downhill, negative velocity, right? Positive slope, positive velocity, negative slope, negative velocity. So from A to B, what do we have? Positive velocity. How about B to C? Is it uphill still?
No.
Don't worry about, we're not doing acceleration, we're just doing velocity. So it's uphill. Okay? At C, it's actually what? 0, right? We don't have to worry about it. Okay? C to D, now our velocity is, we're going downhill, negative velocity. D to E, negative velocity. E to F, uphill, positive velocity. And F to G, constant velocity. Okay, so we're just going to fill that in. It's constant, but it's also what? Positive velocity. Okay, so we have plus, plus, negative, negative, plus, plus, but constant. Somebody does another alphabet? Okay, now, on a position time graph, to get our acceleration, this is where we use concave up, concave down. Smiley face, is it part of a smiley face or is it part of a sad face? Okay, so let's look at from A to B first here. Is this part of a smiley face or a sad face? Part of smiley, so it is positive acceleration. So B to C all the way to D is, well, let's use red. So this is all negative acceleration. Negative. From B all the way to D. Right? That's all concave down. D to F is all concave up. And what's the acceleration going to be here of a line? 0. So we have positive, negative, negative, positive, positive, and then 0. Okay, so let's describe its motion. When is the graph speeding up first? How would we figure out when it's speeding up? When the signs are the same. A times B is greater than 0. So when the signs are the same. So when are the signs the same? A to B, C to D, and E to F. Okay, slowing down. How do we figure out when it's slowing down? When they're opposites, A times B is less than 0. Opposite signs. So when is it opposite signs? B to C, D to E. We should also, when do we have 0 acceleration? F to G. And when is our velocity 0? Okay, when are our velocities equal to 0? So we have E and C. Well, you can't really find the slope. Yeah, well, we don't know for sure. We can't. But we're talking about the slope, right? We're talking about velocity. We're talking about the slope of this graph. So we don't know for sure. So cusp and corners are not differentiable. So we're just going to say E. A cusp? Or well, not a cusp. It would be an edge, like an endpoint. It would be an endpoint. It would be an endpoint, not a cusp. Okay, so we are done the lesson. So your homework is 3 to 7 and number 9.